welcome to my living room. My name is Daniel Steenebrügge. I work at RWTH Aachen. I'm doing my PhD there. And my research interest is geometric knot theory, which deals with knot energies, and what these are, we'll get to that in a minute. I want to talk about the analyticity of critical points for generalized integral Mayer curvature, which is a joint project with Nicole Obermeier from Salzburg. She's doing her PhD there. So, generalized integral Mayer curvature is a knot energy, you might have guessed that, and to better understand what a knot energy is, let's take a piece of rope and tie a knot in it. And then you'll see, no matter how I fiddle around with this rope, I cannot make it into a circle, or any other knot really. At least not until I open this thing up, and then, we'll do rotation, it's a circle. And this is what knot energies should prevent. They don't let me change the knot class without getting infinitely high energy somewhere in between. And with that, you can show for most knot energies that they have minimizers in each class. And these can be viewed as representatives for the knot class. And these minimizers are expected to be nice. And in our case, they are, because you can't really get much nicer than having an analytic curve, can you? How do you prove that? Well, the main ingredient is something called Cauchy's method of majorance, which involves a recursive estimate and some other clever stuff. And to get that working, we need some additional bootstrapping. But if you want to find out, well, you'll have to watch the video. See you then.
Hello, my name is Jesús Castro-Infantes. I'm a PhD student in the University of Granada in the south of Spain. Well, my research interests are related with minimal surfaces and CMC surfaces in homogeneous spaces. Here I'm going to talk about the construction of CMC surfaces in the space H2 cross R via Daniel's conjugate technique. I'm going to divide my talk in two parts. In the first part, I'm going to try to explain some detail about this conjugate technique, and in the second part, I will show you a construction of CMC surfaces with two ends and genus 0 in the space H2 cross R. Well, I would like to thank you, all of you, for attending this event, and especially to Oyoli for the invitation. I hope you enjoy the talk.
Hello everyone, my name is Han Hong. I'm currently a PhD student at University of British Columbia. I've been studying a series of minimal surfaces and surfaces with constant mean curvature, in particular stability theory and index estimates. I'm also interested in spectral geometry like Laplacian eigenvalues and stack of eigenvalues. So in this seminar, I will talk about index estimates for CMC surfaces in general three manifolds. I will split the talk into two parts. In the first part, I will introduce some backgrounds and motivations for our problems. Also, I will talk about some famous results from the history. Then in the second video, I will introduce the new theorem we obtained recently, as well as the proof. And if time permits, I will talk about some examples and applications, as well as its connection to isoperimetric problems. So see you then.
Hi everyone, I'm Romain Petrides. I'm maître de conférence at Université de Paris in France, and I work in the Mathematics Institute of Jussieu in geometric analysis. First, I would like to thank Hojo for giving the opportunity to many researchers to talk about their work in this festival. And it's my pleasure now to introduce my talk, Minimal Surfaces and Shape Optimization in Spectral Geometry. We have here two apparently different subjects, the theory of minimal surfaces, modeling, for instance, soap films, with questions such as existence, uniqueness, or stability. And spectral geometry, modeling, for instance, the sound of a drum. In particular, I work in shape optimization of eigenvalues of some operators, such as the Laplacian on a domain. The surprising link between these fields, discovered by Nadirashvili and revived in the past decade by Fraser and Shane, is that extremal Riemannian metrics for eigenvalues are induced metrics of some minimal surfaces. Then we have a way to build minimal surfaces by shape optimization of some eigenvalues. In this talk, I will first give a short survey to introduce spectral geometry and the theory of so-called free boundary minimal surfaces. And then I will explain how to build free boundary minimal surfaces by maximization of the so-called Steklov eigenvalues. Finally, I'll give a recent spectral gap result with respect to the topology in a joint work with Mathiesen. The main consequence of this result is the construction of free boundary minimal surfaces of any finite topology. I will give a detailed sketch of proof, step by step, of this result. And I hope that you enjoy the asymptotic analysis techniques behind this result. See you then.
Hi everyone, I'm Brian Harvie. I'm a grad student at UC Davis, finishing up a PhD in math, and my research interests are obviously in geometric analysis, but more specifically than that, geometric flows, and more specifically than that, the inverse mean curvature flow. Now, many of you know of mean curvature flow, which is an extrinsic flow that contracts surfaces, and the inverse mean curvature flow is an extrinsic flow that expands surfaces. And what I'd like to focus on in my talk are singularities of inverse mean curvature flow. When do they form, and how do we characterize them? Now, if you've studied mean curvature flow, you know that an elementary result for singularity formation tells you that singularities always happen within a prescribed time interval for closed hypersurfaces. And I'm going to be presenting a sort of analogous result for the inverse mean curvature flow. On the question of characterization, it's also well known for mean curvature flow that singularities are always characterized by a blowup in the total curvature. And what I'm going to show is that in inverse mean curvature flow that it's actually not always the case. So there exist surfaces where the total curvature remains bounded up to the singular time so that you get a limit surface without rescaling. It's very strange from the standpoint of PDE. So I think if you've worked on singularities for any geometric flow, it's something that you'll be interested in. There's a lot more work to be done here, and I hope that you are interested enough to give my talk a watch and maybe come to the question session. So thank you, and hope to see you online somewhere.
Hello everyone, my name is Beomjun Choi, and I'm very glad to meet you. I'm a postdoc at the University of Toronto, and I'm working at geometric flows such as the inverse mean curvature flow, the Ricci flow, and the mean curvature flow. And in this conference, I'd like to talk about the inverse mean curvature flow and its application. I think perhaps the most important or famous application of this flow is the proof of Riemannian Peano's inequality by Huiskin and Ilmanen. And this inequality describes how an area of the black hole should constitute towards the total mass of a gravitating system. And I will explain how the flow leads to a proof of this spectacular theorem. And I will also explain an unpublished result of Huiskin, which relates this mass with the isoperimetric constants of the space. And in the second part of my talk, I will explain my results of inverse mean curvature flow of non-compact hypersurfaces in Euclidean space. Solutions in Euclidean space, if it's non-compact, that is very closely related with its tangent cone at infinity. That's mainly because of the special scaling property of the inverse Minkowitz flow. I will explain in detail in my talk. Moreover, the same idea applies to the singularity of the flow, and if we take the blowing up sequence and take the blow up, the blowing up tangent cone also evolves by the same inverse Minkowitz flow. So that's all. Thanks for your attention, and I hope to see you soon. Thank you.
Hello everyone, my name is Nicolas Marque. I'm a postdoc student in the Institute for Mathematics in Potsdam University. And one of my main objects of study is geometric analysis with a big interest in conformally invariant problems and how the conformal invariants impact the analysis of these problems. This will of course play a role in my talk because I will deal with the Willmore problem, which is a conformal invariant problem. This talk will be divided into two videos. The first one will be a bit lighter in mathematical details, and I will try to introduce the object. I will introduce the definition of the conformal invariants, and to give you a feel of this object, what they are and how they behave under the conformal transformation. The second part will be a bit more technical because I will deal with the analysis first of a Willmore immersion and then of a sequence of Willmore immersions. I will try to show the compactness and or something which approaches compactness. By the end of this talk, I hope that I will have convinced you that the Willmore problem is an interesting problem on its own because it displays some beautiful and sharp analysis with some exotic phenomena which are a consequence of the conformal invariance, but also that it can be used to study of the problem either as a case study in the case of the Marque problem or as a tool for for instance, for determining the best eversion, the optimal eversion of the field. One thing before I conclude is that during my talk I will put references in brackets, and if everything goes well, you should find the exact bibliography in the description of the video. So before I leave, I would like to thank the organizers and to thank Ojoli for having given me this opportunity. And so thank you very much, and see you on my talk.
Hello everyone, my name is Mikhail Karpukhin and I'm postdoc at Caltech, and I'm going to be talking about minimal surfaces, eigenvalues for Laplacian and harmonic maps. So let me give you a quick introduction into the problem. All right, so first I'm going to be considering a very simple case of a closed Riemannian surface. On such a surface you can solve the for Laplacian eigenvalues, and it's a very straightforward application of functional analysis to show that you have a discrete spectrum, and a spectrum is just formed by eigenvalues, right? So you look at the functions f, which satisfy this condition, and the lambdas for which they exist in non-trivial solution form this sequence. And the problem we're considering is optimizing this eigenvalues. In particular, I'm going to be considering eigenvalues multiplied by the area, right? So this is the optimization problem we're going to be looking at. For a fixed surface M, we're going to consider this a product of lambda k times the area as a function of the space of metrics. In particular, I would like to maximize this quantity. And very significant feature of this problem is that critical metrics of such functional correspond directly to minimal immersions of our surface M to some sphere Sn. And this correspondence is very fundamental, and it allowed to, first of all, use techniques of minimal surfaces to gain information on this value and critical metrics, and moreover, to use spectral theory information about those bounds for lambda k to glean some more insight into minimal immersions. So this sparked a huge research in recent years, and I'm going to be reviewing some recent results in this area.